Chapter 1, Section 5, Addition of Real Numbers. We're going to talk about what happens on a number line when we add and then adding without a number line, but I'm going to talk about that. There's some rules that you can follow. They're kind of complex rules when you put it all together, but I think if you can get the visual idea of adding on a number line, you can do that on larger numbers too, and we'll talk about that a little bit. And then we're going to get into problem solving. Since we have a number set with negatives in there, we have all our fractions, which are all the rational numbers you can write as fractions of two integers, and even irrational numbers, which is the real number set. We can use that to our advantage in problem solving. We'll talk about that a little bit. And then probably one of the real important things in algebra is combining like terms, which is really a shortcut method that they're talking about, but really what it is using the commutative, associative, and distributive laws to strategically be able to simplify expressions and problem solve and eventually solve complex equations and stuff. So let's start with adding on a number line. When we add A and B on a number line, we start with A and move according to B, right? If B is positive, that means you go in the right direction. If B is negative, we move to the left. If B is 0, it means we don't move at all, we just stay at A. Now I'd change this a little bit. I kind of like direction on all of this, so I don't have to think of two things. One is I just start at 0. And when I have a negative 4, that means I go to 0, excuse me. And that would mean I would move to the left because it's negative. It goes to the left 4, and then I'd end up at negative 4. They just say start at that first number, which is fine. And then to add this next one, I have a positive 9, which means that from a negative 4, I'd move 9 units to the right. And where you end up is the answer to that addition. In this case, it'd be 5. So if we had this example, 3 plus negative 5, where I would go start at 0, you go 3 to the right for the positive 3 and 5 to the left for the negative 5, and you'd end up at negative 2. And then this other example here is where they're both negative. I'd start at 0, I'd go negative 4, which is a 4 to the left, and then I'd go another 3 to the left for negative 3, I'd end up at negative 7. So they kind of covered all the things that can happen in addition. You end up with a positive answer or a negative answer, or negative and a negative ends up negative, and so on. And they're going to talk about some patterns that happen and those kinds of things, which is cool to look at. But you know, if you get this, in fact, I would recommend that you draw these out, even the simple ones when you know the answer to them, is to use this strategy of a number line and draw it so you can get it into your head that that's really all I need to understand for addition. So when we get to things where I can't get exact values, I'm not going to look for exact values for when I get into fractional stuff. But again, if I had that idea that, hey, I start at 0 and I got a negative 5.2 that I'm adding to 0. I start at 0, I move to the left, negative 5.2, and then 0 means I'm going to not move anymore, so I stay right there, so my answer's there. Now they give us this set of rules, and this always works, but it seems like a mouthful and a long thing to remember. But if you think about the patterns, and if you think about when I'm talking about this, think about that number line again in what's going on. Like the first rule, positive numbers is add as usual, the answer is positive. Well, if I'm adding positive numbers, I'd start at 0, I'd go to the right because it's positive, and then I'd go to the right again if there's another positive number. Obviously, I'm going to stay on the right side of 0, so I'm going to get a positive result. That's a good way to explain this first rule rather than memorizing something. if I add negative numbers, if they're all add are negative numbers, is they say add the absolute values, where what is the absolute value? Is the distance from 0, right? Well, if I think about that with negative numbers, I start at 0, and let's say I added -5, I'm going to go to the left 5. That's the absolute value of -5 is 5, but I go to the left. It's got direction from the negative on it, and then I'd go another negative and another. I could keep doing that. Guess what? You're going to stay on the left side of 0. You're going to end up with a negative sum to that addition. And then they go through this stuff where I have a positive and a negative number. It says subtract the smaller absolute value from the greater absolute value. In other words, you look at the number, which one's a shorter distance from 0, which would be the smaller absolute value. Absolute value means distance from 0. And then you take the bigger absolute value, the one that's farther away from 0, and then you take their difference, which means you subtract them. And if the positive number has a bigger absolute value, or the positive number is farther away from 0 than the negative one, hey, guess what? You're going to stay on the positive side of 0. That would be the same thing as saying, hey, I got a -5 plus 7. Well, I could go, that means I'm going to go to the left 5, and then I'm going to go to the right 7. Which side of 0 am I going to end up on? Even if I said I got a -222 plus 400. -222 to the left, 400 to the right. Which side of 0 am I going to end up? If you hang on to that visualization in the number line, most of your issues with this should go away. And usually I don't see any students have problems with addition until we start talking about multiplication, and then there's some rules about multiplications. You know, like if there's two negatives multiplied, you end up with a positive. So then we get it confused with that. So really hang on to addition. The picture, or basically the diagram or picture I can draw of any addition, I can draw very quickly on a number line. This B, it says if the negative number has a greater absolute value, or another way to say the negative number is farther from 0 than the positive one, hey, I'm going to go a long ways, a certain distance to the left of 0, and I'm going to go a shorter distance back. I'm going to stay on the left side of 0, still have a negative number. And then it says if the numbers have the same absolute value, the answer is 0. And those are called additive inverses. So if I went -5 plus 5, I go -5, I go 5 left of 0, and then I go 5 back to the right from there. I'm going to end up right where I started, which is 0. Okay? But they give us a rule for that. And that number's 0, and then they start giving us a special name for 0. And they don't do that just because they want to use more ink and say, hey, let's give a real special name to 0. We're going to use this identity property of 0 to deal with addition in ways that I can get rid of addition by basically they're defining if I have any number, A, any real number, and I add 0 to it, or 0 plus any number is just equal to A. Now I could say, well, obviously 2 plus 0 is 2, 0 plus 2 is 2, you know. But in mathematics and sciences, they can't say, well, hey, that's an example. What about 3? You know, what about 4? What about 1/2? They could keep on going on, and you could always have another one because there's an infinity of numbers. You can't prove things that way. So they did prove this algebraically, did a proof. So we're going to take that as a law so that we know that anytime you have a variable plus 0, it's really the same as that variable. In other words, it's like the addition went away, and we'll use that to our advantage when we're solving things. And it's called the additive identity, or the identity property of 0. We have one for multiplication, which is the identity property of multiplication, which is 1. 1 is that magic number that when I multiply by it, I get the same thing back. Looks pretty similar to this identities act similarly, only this one is for addition right here. So they give us a property for that. Then they go into examples adding without a number line, and I would determine sign before I do anything here. And then, and also you think about it, if I do this, they're both the same sign, I can say, hey, I'm going to be on the left side of 0 on this one. I know I got a negative. Now, did I go the same direction each time? Or in other words, did I really add the distances as I went? And yes, I end up at negative 19. Where B, I go a smaller distance to the left, and then I go to the right, a bigger distance. What's the sign of this one? It's going to be positive. Now, it's not going to be 1.4 plus 8.5 and say positive, because I went to the left. It takes me 1.4 to get back to 0, so it's going to be 1.4 less than 8.5 on the positive side. In other words, you subtract those and have a positive. This one, I go 36 to the left, 21 to the right. Am I going to end up in a positive or negative? It'll be negative. This one's equal to 0. These are additive inverses, which they're going to define here in a little bit. But I go the same distance to the right and then back to the left. The same distance I end up back at 0. If I add 0 to anything, I get that same thing back. That's this property right here for E. And then even with fractions, sometimes it's harder, I need to maybe get a common denominator before I can really do any addition and take the maybe out of that. That's how we have to do addition of fractions. So I might want to make sure I get a common denominator here first, which would be 24. Rewrite each fractions as 24th. And then I'm going to say, hey, I got the same size denominator. Now I know which one's bigger or which one's farther from 0, or another way to say the absolute value, which one has a bigger absolute value. And then you're going to be able to determine the sign and then add the numerators. Okay? So when I change this to 24ths, that's going to be negative 15 24ths, and this will be 16 24ths. So it's going to be a positive 1 24th. Okay? They go through this I talk through it quickly. Here it is all the way here, right? They show us, well, we got to get the common denominator. We've gone through that lesson on how to do that. So, and think. They're saying think here. They're saying think about absolute values and, which one's doing. They're applying those rules that they gave us, which is if that's what you got to do, go for it. But I sure like thinking of a number line. Thinking of just a visualization, and then I know this is positive, I know this is negative, and I know how to get there just thinking about how I would drive that little line from 0 on a number line. So, but now we're going to get into some strategy. What if I'm adding a whole bunch of numbers here? Well, I can use the commutative law of addition. As long as it's all addition, I can change the order any way I want. And I've done this in class a lot of times when you list numbers by grouping them into groups of 10 if you can. And that's using the commutative and associative law. Well, what they do here is they reorder it. They put all the positives first and all the negatives next. And then they group them, which is the associative property. And they say, well, let's just add this group of positives and let's add this group of negatives, and they get this. And you would do that. Now, I'm going to argue with this problem solving a little bit here. I like things that add to 0. Man, 0 is easy to add. You might see right here I got a negative 5 and negative 2. Hey, that part right there, because I know I can use commutative and associative, I could group these differently. And I could say, hey, even when I'm at the beginning, I might notice that these two add to a negative 7 and I got a positive 7. What do these three add together right to? Is 0. So now all I got is 15 plus 14 plus negative 12. To me, that seems to be a very good strategy because there's less math that I have to do. Not really less math, but I'm looking for things that add together into obvious, simple sums like 0. And I'd end up with the same sum there, which is 17. Now they go into problem solving where they say credit card interest rates let's read this here. During a 4-week period in 2011, the national average credit card interest rate dropped to 0.9%, then rose to 1.6 or 0.16%, stayed the same, and then dropped to 0.2%. Not 2, excuse me, I'm adding words to it. Dropped this amount. Let's read that again, which a lot of times, you need to do this, is to read these again and make sure well, they tell us that in this national average credit card, it dropped or went down 0.9%, if I'm reading this again. And then it rose or went a positive 0.16%, and then it dropped 0.2%. Well, we can represent those numbers with this opportunity using negatives now. Well, drops are going to be negatives. Rising in value will be positive, and here's another drop, which should be negative. So I end up with an addition, because what are they asking? Because they want to know how much change happened over these 3 periods here. So we put sign to that. The first change was a negative 0.09. The second change was 0.16. That's positive. It went up. The third change was 0. They said there was really no change. I said 3 periods. There was really 4 periods talked about. And then the fourth change was a negative, or went down 0.02%. So all we need to do is add these together, and that'll be my total change for that length of time. So you do the addition, and I might want to do that strategy. I can add these two negatives together. I'll get a negative 1.1, and then I have a positive 0.16. I know I'm going to have a positive answer because this one's farther from 0 than a negative 1.1. Okay? So they say that it actually rose at 0.5%. Now, right here at the end of this section is probably one of the biggest used things in algebra, and it really is. They use this combining like terms. They want you to get very efficient and have strategies and look for ways to deal with this. But really what we're using is a distributive law to factor, which we haven't really talked that much about. A little bit before factoring is breaking something into an addition into a multiplication, that we can actually do the addition in the grouping symbol. That's the goal, so we could simplify some expressions. So like here in A, we have combine like terms to form equivalent expressions. Now, what they're talking about is like or similar and terms are real the language we need to learn. Combine, collect, like terms, or these are the words that come up a lot. But the reality is here for what we're doing is we're applying the commutative law if we need it with the associative law and the distributive law. Now in this case, I don't need to change the order. I don't need to group anything differently. But I can notice that this one has a variable of x in both of these. Remember, these are factors, really. This negative 7x is negative 7 times x. This 9x is 9 times x. They're parts of a multiplication, which are called factors. And they have a common variable factor. And it isn't just always just looks for the same, that they might have other common factors, but there's a strategy involved in here to be able to do the distributive law to say, hey, can I take this and get so I can do something in the parentheses here to actually do the addition. In this case, add negative 7 plus 9 and then take it times x. Well, that's a distributive property. I have a common factor of x. I can bring that out and then that x, if I take it back, which is what we're usually used to see in the distributive law, if I took this x times this quantity here, I'd go x times negative 7x, I'd get negative 7x. Or x times negative 7, I get negative 7x. And x times 9, I get 9x. Well, luckily I can go in reverse of that, and that's what they do, is called factoring. And now I can do this addition in this parentheses. Negative 7 plus 9 is a positive 2, so I get 2 times x. So in other words, when I combine like terms, sometimes simplify this expression, there's a whole bunch of words that they put around this, is I can apply the distributive law and write this expression as 2x. Now in this case with b, we have 2a plus negative 3b plus negative 5a plus 9b. Now notice that the first thing they do is they start changing the order, and they put the 2a and the negative 5a together at the beginning. And think about, why would they do that? Because they have a common variable factor right here of a. Then they have negative 3b and positive 9b, and we can add those. So then they use the distributive property. So they use the commutative property, and really what they don't show here is, well, I need to treat this as a group, and then I can factor that or use the distributive property. They kind of just left out the associative property here. But what I can do is then rewrite this as an addition that I can do. That's the goal of using that distributive property of factor, is I want to be able to perform some operations here to simplify this addition. And I get 2 plus negative 5 all times a, which is negative 3 times a. And here I get negative 3 plus 9 all times b, which is 6 times b. And let's see, what's the next one? C right here. We got 6 plus y plus a negative 3.5y plus 2. Well, it works with constants too. And we're going to get, when we get into exponents, I could actually put a variable there and put it to the 0 power, but we're not going to, we'll talk about that later. But I do want to get it in order so I can perform the addition, really. So they use the distributive here and they get 1. And probably what they really need to point out here, there's no number times y up here. I just have y. What number can I always take times that to get y? Well, it's 1. This is really 1y. It's the same as y. And we're going to need to have that constant involved here when I factor out, that it's not 0 plus negative 3.5. It is 1 plus negative 3.5 then times y, which is a negative 2.5 when I do that addition. Again, get very comfortable with what's going on around here and stuff like that. I'll bring back a lot of stuff on fractions a lot of times. Boy, don't avoid fractions. We need to get really comfortable in working with those. But also this is, you're going to be able to look at like terms. You're probably going to figure it out and be able to do it in your head. This is the important part. Why does this work? Because we're going to use this distributive law, commutative law, and associative laws in a lot of strategic ways to solve problems. And if you're not real clear on all the different ways you can use these laws, that's going to be a problem later on in the class. So really focus in on the whys things are happening, especially here earlier in the course. And that's section 5.